Last time, we took a terrifying infinite product of cosines and collapsed it into something beautiful. Sin x over x. Today, we use that exact same function to crack one of the most famous unsolved problems in history. The man who did it? Leonhard Euler. Here's the problem that broke mathematics for 90 years. Take the sum of the reciprocals of all perfect squares. 1 plus a quarter plus a ninth plus a 16th plus a 25th. Let me show you what this actually looks like geometrically. Start with the square of area 1. Add the square of area 1 quarter. The running total is now 1.25. 1/9 now 1.361. 1/16th 1.424. 1/25th 1.464. The squares are shrinking fast. The sum is clearly converging. But to what exactly? Here's the jaw-dropping spoiler. The answer is pi squared over 6, approximately 1.6449. But why? Why does pi, the ratio of a circle's circumference to its diameter, appear in a sum of fractions? Well, that's what we're about to find out. This problem had defeated every mathematician in Europe for nearly 90 years. Then, in 1734, a 28-year-old Swiss genius named Leonhard Euler sat down with a single function. Our function, sin x over x, and his target, the exact value of the sum of 1 over n squared. And his weapon was an identity connecting sine to an infinite product, the same identity we proved in our last video. If you haven't seen it, go watch it now, because what comes next builds directly on that result. Euler's strategy was to look at sin x over x in two completely different ways and force them to agree. The phase 1 was the Taylor series. We know that sin x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus so on. Now, divide every single term by x. Sin x over x equals 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus so and so on. Since 3 factorial is 6, this simplifies to 1 minus x squared over 6 plus x to the 4th over 120 and so on. Now lock in that x squared coefficient. It's negative 1/6. Write it down. We're going to need it. Phase 2. And this is where Euler made his audacious leap. Start with something you already know. If you have a simple polynomial with roots r sub 1 and r sub 2, you can write it as a times bracket x minus r sub 1 times bracket x minus r sub 2. But if you normalize, divide everything so that the value at 0 is 1, it becomes bracket 1 minus x over r sub 1 times bracket 1 minus x over r sub 2. This is the root factor representation. It works for any polynomial whose value at 0 is 1. Now, here's Euler's bold idea. What if we do the same thing for sin x over x? First, what are the roots of sin x over x? They're the places where sin x equals 0, but not as x equals 0, since sin x over x approaches 1 there. So, the roots are plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on forever. Look at the graph. Every multiple of pi is a root, stretching out in both directions to infinity. Now, Euler paired up on the symmetric roots. Plus n pi and minus n pi combine into a single factor, bracket 1 minus x over n pi times bracket 1 minus x over n pi. Multiply those out. It's a difference of squares. You get 1 minus x squared over n squared pi squared. So, sin x over x, with its infinitely many roots, becomes an infinite product of these factors, one for each value of n from 1 to infinity. Now, Euler assumed this root factor trick extends from polynomials all the way to this infinite function. That was his leap of faith, a breathtaking one, and it turned out to be completely correct. So now we have sin x over x equals the product of bracket 1 minus x squared over pi squared times bracket 1 minus x squared over pi squared times bracket 1 minus x squared over pi squared, and so on. What's the x squared coefficient of this product? Think carefully. To get an x squared term when you expand, you must pick the x squared piece from exactly one bracket and multiply by the one from every other bracket. From bracket 1, negative x squared over pi squared. From bracket 2, negative x squared over pi squared. From bracket 3, negative x squared over 9 pi squared. Add them all up. The total x squared coefficient is negative x squared times the sum of 1 over n squared pi squared from for n from 1 to infinity. Factor out the pi squared and we have negative 1 over pi squared times the sum of 1 over n squared. This is the x squared coefficient from the infinite product side. Now for the killing blow. Both expressions, the Taylor series and the infinite product, describe the same function, sin x over x. So, their x squared coefficients must be identical. Set them equal. Negative 1/6 equals negative 1 over pi squared times the sum of 1 over n squared. Cancel the negatives on both sides. 1/6 equals 1 over pi squared times the sum. Multiply both sides by pi squared. And there it is. Pi squared over 6 equals 1 plus 1 quarter plus 1 ninth plus 1 16th plus 1 25th and so on. Pi squared over 6. Euler proved this at 28 years old. It had defeated every mathematician in Europe for 90 years. And the key to the whole proof was the same sin x over x that lives at the heart of our monster integral from before. Mathematics has a memory. Let's retrace the full journey. From our monster integral, we know the infinite product of cosines equals sin x over x. The Taylor series gives us its x squared coefficient, negative 1/6. Euler's root factor theorem gives us its infinite product form, whose x squared coefficient is negative 1 over pi squared times the Basel sum. Set them equal. Pi squared over 6 equals the sum of 1 over n squared. That's Euler's Basel problem solved. Subscribe, because we're building a mathematical universe, one beautiful result at a time.